Hi, everyone. Today we're talking more about change of angular momentum. Last time we developed that dl/dt torque angular acceleration triangle. Today we're going to actually start utilizing that. Okay, so first we have a light cord connecting M1 and M2 over a pulley of radius r and moment of inertia I. The surface under M2 is frictionless. So first, do the blocks acquire angular momentum while moving? So our reference point, remember, angular momentum is a relative thing with the vectors, right? It's got a relativity to it. So the relative point will be the axle of the pulley, right? So if we are wondering, are the blocks going to acquire angular momentum while moving? The answer is going to be yes. Now, the reason behind that is going to be a little different. Okay? So it's not going to be quite as straightforward as just yes. So if you have rotational motion, right, then you have angular momentum as long as you are moving. Now, if you are moving linearly, okay, you have angular momentum if, right, there is some r cross p, right? Now we also know that you can acquire angular momentum by some unbalanced external torque. Okay, if there is any net torque on the system, then there is going to be some change in angular momentum, most likely an increase, right? I mean, even if it's decreasing, then you still have angular momentum, right? Then it would just be negative. So yes, the blocks will acquire angular momentum because they're going to be part of this system that is going to have torque acting on it. So write an expression first for the net torque acting on the system. So let's do that. Let's see, we have net torque is going to be R cross with the net force, okay? We are saying that our torque is relative to, again, that axle of the pulley. Okay, so let's find our summation of force. We can do that with stack and rack, right? So we'll do summation of force of the pulley, and then we'll do summation of force on the mass. Okay, so on the pull, oh wait, and then we need, so that's mass 1, and we also have summation of force on mass 2. Excuse me. So we have on the pulley, okay, let's say I'm going to call this tension A, and I'm going to call this tension B, okay? So that pulley has tension B driving its motion, tension A resisting, okay? Then on mass 1, you've got M1G pulling it in the direction of motion. That is resisted by tension B. Then for mass 2, it's frictionless, so in the direction that we're worried about, all it has is tension A. So the summation of force of the system, okay, let's see, we've got a positive and negative TB, a positive and negative TA. So all that's left is M1G. That is the summation of forces acting on this system. And then the M1G is acting a radius 2. You can see that there's radius 2, right? So radius 2 from the axis. So we can justify using radius 2 by the fact that when you're using the cross product, okay, you could also say that torque is the perpendicular radius times the force. Remember, we've started using that when we started using cross product with angular momentum. So here is your force, right? Force is down here. There is your M1G. And to get that perpendicular component of the radius, you would use R2, right? So your answer here is going to be M1G R. Okay, so that is what we get for torque. Now it then asks, write an expression for angular momentum of the system. So here this is going to be a little different. Our angular momentum we're going to have a rotational and a linear object, right? So that can be I omega, and it can also be R times mv, right? So we'll actually have to use both of those to use our to get our our angular momentum. So we have the moment of inertia of the pulley times omega, which would be, again, of the pulley. Then we will have mass 1 times some velocity times r, let's see, that would be times r2 also. Yeah. So we'll use v times r2 plus m2v times r2. Okay? And again, we are doing that because the concept of L has that cross product, R cross P. Okay? So let me clean up this a little bit more. If the momentum of M2 is in this direction, then your perpendicular radius would be right here, right? So that would be R2. And then we can really just call this M1G. That is also in the direction of the momentum, right? So you've got the momentum of 1, the momentum of 2. Okay? And they are both off the axis of rotation by an R2 if you were judging by the perpendicular rule, right? So that's why we're going to use R2 for those. So that is the angular momentum of the system. Okay? I know this is kind of jumping step by step. This is really broken up. But now we want to find dl dt. Okay? So let's find dl dt. We're going to take the derivative of this statement. Okay? dl dt equals the derivative with respect to time of I omega plus the derivative with respect to time of m1 vr2 plus the derivative with respect to time of m2 times v times r2. Okay? So now we need to look at, in this scenario, what is actually changing with respect to time. Okay? So our dl dt, the moment of inertia isn't changing. We're not like breaking the pulley, right? So you would have I times d omega dt, which is alpha, right? Then for your m1 vr2, m1, we're not changing the mass. R2, we're again not changing the pulley. So v must be the thing that's changing. So you have m1 r times acceleration. Same for the second mass, m1 r2, then m2 r2 a. Okay? So that is our dl dt that we are going to use for our answer. Okay, pretty straightforward. Now, the last thing it asks us to do is to put number 4 in terms of alpha and simplify. So if we were to do that, okay, we already have I alpha, so that's nice. We want to use the idea that alpha is A over R stemming from this equation, A equals alpha R, right? So we want to use A equals alpha R, right? We're going to substitute A for alpha because we want it in terms of alpha. So that means that dl over dt equals I alpha, already in terms of alpha, plus m1 r2 squared alpha, right? Because we're multiplying a new radius, plus m2 r2 squared alpha. Okay? So that is our dl dt. Now notice that what we have here is we have, if we factor out that alpha, we have dl over dt equals I plus m1 r2 squared. That's the moment of inertia of a particle, which we would assume the box is a particle in this case. So m1 r2 squared plus m2 r2 squared times alpha. So if we call this the moment of inertia of the system, then dl dt equals the moment of inertia of the system times the angular acceleration of the system, which also equals the summation of torque, and we just kind of recreated the triangle by showing that dl dt equals I alpha equals summation of torque. All right, good. So that is another demonstration using the LTA triangle. Just a refresher, a reminder of where we're getting these relationships from. That's from our last video, that these all can equal each other one way or another, right? So if you have one, you can find the other, just like we demonstrated, right? We had torque, then we found angular momentum, took the derivative. The derivative of that turns out to be I alpha, and we know that I alpha equals the summation of torque. So kind of did that all over again. Now this one's a little bit more complicated. We have a particle that's now a sphere, and the rod now has mass. So we have a thin rigid rod of mass capital M and length lowercase l, pivoted in a vertical plane without friction about the center of the rod. Two spheres of radius r1 and r2 and mass m1 and m2 are attached. Assume the center of mass of each sphere is located at the end of the rod, and the system rotates clockwise. It may be helpful to draw the scenario. It would definitely be helpful to draw the scenario. So let's do that. We have rod. Okay, the center of mass of each sphere is on the ends. Okay, we have here, let's say that is M1 with a radius R1. Then here we have M2 with radius R2. Then we know that it has length L, it pivots about its center, and the rod has a mass uppercase M, right? And then rotating clockwise. Now, letter A says for an angle theta with respect to the horizontal, derive an expression for dl dt in terms of m1, m2, g, r1, r2, and l. Okay. So let's establish our angle. Okay, we have, here's our horizontal. Okay, there is our angle theta. So what we're going to do here is we are going to recognize that if we look at the triangle, I don't have any room to write on that slide, so let's do this right here. If we want dl dt, okay, we can find torque, or we can find I alpha if we need to. Okay, so recognize that dl dt is just the derivative of rmv divided by dt. Okay, here we don't really have evidence of any of those changing, and also none of these terms really fit nice and neat into the derivative of r, derivative of m, or derivative of v with respect to time, other than g kind of working into dv dt. However, another way to find dl dt is to simply find torque using your cross product r cross f. Okay? And again, we are going to use the shortcut of r perpendicular times f. Okay, so that is our method. I will talk about I alpha later in part B. So if we want to do r perpendicular times the force, let's identify what the forces are. Okay, so the forces are gravity. Okay, you've got here, oh, that's bad, my hand's stuck to the screen. There you go. So you've got that right there. That would be, this is m2g, right? And then down here, you have m1g. Let's get that out of my way. Right there. That would be m1 times g, right? Now we notice that the force and the radius are not perpendicular, right? Because the radius for torque, remember, all these radii have, radius vectors have different definitions. So the radius vector for torque is the vector from the axis of rotation to the point that the force is acting. Okay? That would be this radius right here. But our perpendicular component of the radius would be right here. So what we can do is, to find our perpendicular, we could do r cosine theta. And r in this case is not an acceptable variable, right? We have r1, that's the radius of the sphere, and r2. Both of those haven't even been mentioned yet. But we can put it in terms of L. We could say that instead of r cosine theta, this is L over 2 cosine theta, L being an acceptable variable. So we will use that for our perpendicular, and our force is going to be the mg's. So let's set up our torque here. So if we say that dl dt equals the summation of torque, we know that the summation of torque is going to be the force on sphere 1 times r perpendicular for 1 plus the force on sphere 2 times the perpendicular radius for sphere 2. Okay. Now, the force on sphere 1 is actually pointing down against the motion. But remember, torque is not just with or against motion. Torque has a defined positive and negative. When we're talking kinematics, you can kind of fudge the numbers, right? Like you can just say direction of motion is positive, direction of acceleration positive, or you can just define your positive however you want, as long as it has meaning, right? Here, torque has a specific definition of positive and negative. Counterclockwise is positive, clockwise is negative, every time. So torque, this m1g is causing a counterclockwise motion, right? That is opposing the clockwise. So this would cause positive torque. So this would be a positive m1g times L over 2 cosine theta, which is our perpendicular r. Now, would we add or subtract that other one? Well, so they are in the same direction, right? So you would think that they would be the same sign, but since we're talking about rotation, they may be in the same direction, but m1g is going to encourage counterclockwise motion. m2g encourages clockwise motion. So no, this we are actually going to subtract m2g times L over 2 cosine theta. And that is our torque. And yeah, we don't have any values for this. Yeah, so that is our dl dt that we were supposed to solve for using summation of torque. All right, good. And I would honestly, to simplify that, I would actually factor out a cosine to show that this is, you've got force times radius. Actually, you know what I would do? I would do force. You've got m1g minus m2g, right? That's the summation of forces times L over 2 cosine theta. So you've got your force, your radius, and then the cosine theta right there. So that's how I would simplify this if you were looking to simplify that answer. All right, so that was letter A. Letter B says, is alpha constant as the system rotates, and can basic kinematic equations be used? So let's look at this concept here, right? We have this figure. So is alpha constant? Well, we know that with our triangle, right, the derivative of angular momentum with respect to time equals the summation of torque and equals I alpha. So if we can see here that if there is torque, there is angular acceleration. But what if torque is changing, right? So here, if we look down here, oh, scroll. Come on now, move. There you go. So if torque is changing, then I alpha must also be changing, right? And torque is not going to be the same all the time. No, there's not a t variable in there, but there is a theta in there, meaning that as this thing rotates, okay, as that is rotating, with every change in theta, you have a change in torque. And if you have a change in torque, that means that you have a change in I alpha. Well, as we rotate that, we're not changing the mass of the spheres, the mass of the rod, the length of the rod, or the radii of the spheres. So the moment of inertia can't be the one changing. It's got to be the angular acceleration. So knowing that a changing torque is taking place with every change in theta, that means that there is a changing angular acceleration also with every changing theta. And to finish that question, can basic kinematic equations be used? No, they can't. If you're trying to use the angular kinematic equations via theta, omega, and alpha, those don't work because they have the assumption that alpha is constant, right? You have to have a constant angular acceleration. Even if you want to analyze the linear components of this situation, you can't do it using general kinematics, using the x, v, and a equations as they're generally stated, because those also have the assumption that linear acceleration will be constant. And if angular acceleration isn't constant, neither is linear. So no, that's why we didn't even touch I alpha in this triangle, because it can't be used, because I alpha assumes constant acceleration even with that equation. Now, letter C says write an expression for the moment of inertia in this system. So we may not be able to use the alpha, but we can still find the moment of inertia, right? So let's find that moment of inertia. Okay, so the moment of inertia of the system is going to have 5 parts. Okay, we first have the moment of inertia of the rod. Okay, that is mass of the rod, length of the rod squared divided by 12. That's just the rotation of a rod about its center of mass around its center. Then we have the what is the term? Solid sphere. Solid sphere, not a shell. A solid sphere rotated about its center of mass, but we'll use parallel axis theorem to find the rest. So the moment of inertia of our spheres, we're going to use 2/5 mr squared, but then we also have to add md squared, the mass of the sphere, times the distance from its center of mass to its new axis squared, because this is the parallel axis theorem, right? If the axis changes in a parallel fashion, then you are able to give it a new moment of inertia pretty simply. So you've got 2/5, let's say that is m1 r1 squared plus m1. Now our distance here is L over 2, right? L over 2 squared is L squared over 4. So I'm going to put that all in one big term, m1 L squared over 4. And then we're going to repeat the process for mass 2, r2 squared plus m2 L squared divided by 4. Okay. And that is your moment of inertia for this system, right? So that sums up this kind of complex problem. Okay, we had to use torque instead of dl dt, and we didn't even touch I alpha because alpha was not going to be constant. Another reason that you wouldn't want to use dl dt, right, is because this would lead you to make the assumption that you've got to do rm dv dt, and what do you know? dv dt is a, which is not constant. So that is why we wanted to use this to make our point, to solve the problem. All right, so one extra example. We've got time because I'm not bound by class periods on YouTube. So an example problem for the triangle, one more. We've got a 4 kilogram mass attached to a light cord wound around a pulley that is a hoop with radius 8 centimeters and mass 1 kilogram. The system starts at rest. So first, what is the net torque on the system about the axle? So this is the system we're working with, right? Pulley has mass capital M, block has mass lowercase m, radius r is the radius of the hoop pulley. So net torque on the system. Okay. What I'll do is I'll actually do a stack and rack again just to show that we are going to do r cross summation f. Okay, just kind of drill that point in. So our summation of force, we'll do summation of force on the pulley, summation of force on the mass. Okay? So summation of force on this pulley, the only thing pulling on it is the tension. Okay? So that is all we have going for that. But then for the block, you have M1G minus tension. Lo and behold, tension can almost always be canceled out. So the summation of forces of the system is M1G, leading us over here to say that torque equals, we'll say R perpendicular times M1G. What is our R perpendicular? Well, if you have the M1G acting here, that radius R right here, okay, that is going to be perpendicular. It's kind of hard to show that. I mean, if you can imagine 3D, okay? But that is going to be your perpendicular radius. You're not going to go from the radius or from the axle. I guess you'd really go from this axle, right? You're not going to go from this axle to the box because that is a little bit too complex, right? That's tough. So what we're going to do is we're going to use that perpendicular trick, right? So R perpendicular is the radius of the pulley. So that means that your torque for this system is mgr, which, since we have values, we can put that in. The mass of the block is 4 kilograms. Right? 4 kilograms, 9.81 times the radius of 8 centimeters. You should get 3.14 Newton meters. Okay? So that is the net torque on this system. Okay? If we have sigma out there, right? That is the net torque on this system about the axle. Now we want to determine the angular momentum in terms of velocity. They're not going to give us velocity because that establishes that it is a point in space, right? So we're just saying there's going to be some velocity to this. So now let's keep in mind that angular momentum is R cross P. But again, that R is going to be tricky, so we're going to say that this is the perpendicular radius times mv. Okay. However, we have two objects here, so that's going to make this a little bit more complicated. If we want to show that, we can say that this is the mass of the pulley times the radius of the pulley, plus the mass of the block also times the radius of the pulley, because we're using this perpendicular radius loophole, right? All times the velocity, okay? So now that we have mr, big mr plus little mr, all times velocity, those actually have values. So we can plug that in. Let's see, we've got 1 times 0.08 plus 4 times 0.08 times velocity. So you get 0.4 kilogram meters times velocity. Okay. So that's going to be our angular momentum in terms of v. Okay. Now, what is the acceleration? I would say let's take the derivative of angular momentum instead of doing I alpha. Okay, we've already got everything really close to set up for this. So we've got dl over dt is the derivative of rmv with respect to time, which means we've got rm dv over dt. Okay. We also need to remember that via the triangle, this equals the summation of torque, which we already have. So this is going to be pretty simple. If you take that concept, okay, that means that your acceleration is the summation of torque divided by the system, okay? It is the mr of the system. Okay? Remember, we already have that too. That is right here. Okay, we already did that because we had the mr of the system right here. Mr of the system. Okay. So we already know that that is 0.4, right? So you've got 3.14 Newton meters from the torque. You've got 0.4 kilogram meters from the mass and radius of the system, that means that you're going to get 7.85. 7.85 meters per second squared for the acceleration. Okay? Now, that perpendicular radius trick is really cashing in on all of these problems. Okay, it really helps a lot to be able to find the perpendicular component of the radius. Instead of doing the cross product, you're able to, instead of the cross product with two complex vectors, right, you're able to simplify it and not include the trigonometry in a complex situation. So that is really helping us out here. All right, so that is all we have for the change of angular momentum, and we're going to continue on next time with the conservation of angular momentum.